Welcome to module 12.4, and now we will start understanding the OS interface in a great detail. Now we know we have written the compiler. Now we know how to translate a JAK file to a VM file. We know how to translate a VM file to a ASM and then assemble ASM to this, and then so we are quite now familiar with all these things, right? So now let us see, before we before we proceed further, we would now understand what is the OS interface for a given program. Already we have seen many programs, right? So there are so if you actually look at the programs, some of the programs that we would like to experiment here, let us go to the tools directory here. Let us take one such example. So I am just taking the example of one of the programs, one of the JAK programs here. So let us say now if you look at this JAK program, this is called array.test. This is available in the projects 11 directory, projects 12 directory. So this is available in your Nantu Tetris projects 12 array test main.jak, right? Now if you look at this program, there are lot of routines that this is basically taking. For example, array.new, similarly array.new here, then some dispose routines of C and B, where C and B, A, B, C are arrays. So this is equivalent to array.dispose, etc., right? So essentially that means these array functions, as you see here, or methods that you are seeing here, we are actually basically using something that is available with the operating system, right? So if I say array.new, so this is something like that is available with the operating system, right? So the array, all these array functions, we assume somebody else is giving us, and who is giving us? The operating system is giving us, right? Similarly, if you go back to the C programming language, you will have printf, scanf, all these things. These are given by the operating system. That's why you include stdio.h, and inside stdio.h you actually see these functions there. So now to go back to where we are, every program basically has two components. Component number one is it has the whatever you are writing, it has something that the original user code, and there are calls to operating system routines. The same thing is what we are seeing here. So we are now having lot of OS functionalities that are available, and we basically use these functionalities. These are provided to us as VM files. So you write, say, main.jak, as I have shown, you compile this, you get the .vm files. These .vm files will have certain calls for keyboard or math functions or arrays, and these are already provided to you by the operating system. Okay. Now where do you find these files? So these files are available in the tools/OS directory. So in the Nantu Tetris, if you have a projects directory, and of course you would have the tools directory. So tools.os, and so in the tools.os directory these files are there. So I will just show you the tools.os directory as we see here. So if you just go back to this is the OS directory. Now if you just see array, right? Now you see array.new here, and then you see array.dispose here. So two functions are part of this, array.new and array.dispose. Similarly, if you go to math, for example, you have math.init, right? And then you have several other functions So, large files, right. So, you have several functions inside math. Okay. So, if you just scan through this entire thing, you will find many functions here, right. For example, math.max, right. So, like that. Okay. Similarly, your keyboard. So, keyboard.init, keyboard.readchar, keyboard.keypressed. Okay. All these things are there. Now, you are free to use these as a part of your Jack file, and automatically when your compiler will basically call these functions, right. It will just say call of this function. So, when we go back to say the way, let us see this example. When you look at this is the array dot this is the Jack file that you are seeing. If you see the VM file for that, right, if you see the same VM file for this, you see that this has basically this is the VM file, and this has basically called array.new. Okay. So, you are seeing array.new here, array.new, call array.new 1, and where is this array.new? This is there in the array.vm file, right. So, so that is what. So, there are many routines that you can write as a part of your Jack code, and the compiler will automatically take those code from these VM files. This is how you are writing your printf, scanf statements in C, and finally, you are not coding printf and scanf, somebody else is coding printf and scanf. Who is that? The operating system. And so, that is why you include stdio.h, right, and in the stdio.h file these prototypes for all this printf, scanfs are there, and that is how they are written. So, somewhere we need to basically link, right, you need to link your Jack file with the array these VM files. So, that is what we call as linking. Okay. Now, we will go ahead and see something. Before we go into linking, we also need at the compiler stage, we also need to understand certain stuffs. For example, let us take this Jack command. Let let length is equal to keyboard.reint how many numbers, right. So, this will basically land us up with a call keyboard.readint with one parameter. What is this parameter? This is going to be a string constant. So, this parameter will be a memory location, say 1000. So, this will be a memory location which is 500, for example. On 500, what you will see? You will see a link to 1000. So, from 1000 onwards, 1000, 1001 like this, we will have H, O, W, blank, M like that. So, this will basically give this call keyboard.readint, the parameter that should be before you call keyboard.readint, the parameter that should be on the top of the stack should be 500, right. Sorry, the parameter that you see on the top of the string should be 1000. So, what it will do, the moment you should not be there, the moment this call keyboard.readint is called with that parameter 1, on the top of the stack it will be 1000. So, immediately this will go to 1000 and start reading the string till it finds a null. Okay. So, this will read the string, and then it will that will be passed as a parameter. So, the keyboard.readint is going to read this string. So, what is given as an input to keyboard.readint is the starting address of the string. Okay. Right. That is what. So, in the real compiler, if you see, this would have been a string constant, and how do we process this string constant? We just create string length number of locations using string.new, right, and then we append one that will return one null string. So, that will return the string.new would have returned 1000 with some 20 spaces. Let us say this is some 10 characters or 12 characters. So, 12 characters here, and it will be initialized to null. but it will have reserved space for 12 character. Now you start appending character by character, H, then O, then W and all. So this particular string constant is actually a term. This term will basically return you on the top of the stack this 1000, and that 1000 is given as an input to this, as an input argument to this, and so that is how this keyboard.readInt will start reading it. So just to give a very quick grasp of it, this is what we did for the string constant, as you remember earlier. So if this is the string, how many numbers in our case here, and so you push the constant string length and you call string.new.1. So let us say this is 20, so 20 locations are created for a string, say starting at 1000, 20 locations are created and initialized to null. That is what string.new done. And what you do for I equal to 0, I less than string length, you keep on pushing the character constant to this, and you start appending the character. So to this H will get appended, OW. So you are calling this string.append char also. So we are using these string functions. Where are these string functions? These string functions are available in string.vm. This is a operating system file, right? These are available in string.vm as you see here. Okay. Now, okay, so in compilation, one of the things that you should always keep in mind is that if you create some memory before the end of the program, that memory should be released back. Otherwise, you will end up with what we call as the memory leak. Please remember this term, and whenever you study compilers or operating system, especially compilers, you may ask this, you may get a better, much more deeper understanding of memory leak. So what is memory leak? If I basically create some memory for my program, in this case I have created a memory of say 20 locations for storing this how many numbers, right? This should be released back to the operating system. So what does string.new do? Basically, if you go back to string.new here in the code, so this is on the OS. Let us go to string and let us see string.new. It actually allocates call memory alloc. So it actually allocates memory, that many memory for storing the string. So it actually calls the operating system. String itself is an operating system routine. It calls the memory management part of the operating system and says, give me some memory location. So the memory, the operating system per se will maintain something called the list of freely available memory. From that it will take some memory and give it, this memory.alloc will give it to string.new, saying this is the total number of locations I have, from this you take this much and you use this, and this is from this starting address. So it is the responsibility of the program to return it back to the memory, because later somebody else can use that memory, or you yourself can use it at a later point of time. So any memory that we request from the operating system has to be disposed of, right? So in this case, so that is something that you need to understand. So whenever, in this case, when you when you say keyboard.readInt, it is taking, you are creating some memory location and giving it to keyboard.readInt. Now please understand who is going to return it back to the memory, right? So that is where you need to understand the routines in very great detail. Now if you see that this keyboard.readInt basically reads this string, and after reading this entire string it goes and displays on the screen. If you remember, it will say how many numbers, and then this keyboard.readInt itself will dispose it of. So your program is, which uses keyboard, this is your program, let length equal to keyboard.readInt is a statement in your program. Your program creates that space for that how many numbers, and it calls keyboard.readInt. The keyboard.readInt actually disposes the memory, right? So if you go back to this keyboard, if you look at keyboard.readint, okay, let us quickly search for that. Yeah, so the keyboard.readint file, if you see that, you see that it disposes the string, right. So this is how when you call OS routines, you should understand what the OS routines is doing specifically from the memory handling point of view. Otherwise, what will happen is you will land up with memory leaks, right. Memory leaks is that you have taken the memory and before you finish you have not returned back the memory. So the operating system will not know that that memory is available. So that memory you do not use it, but you are not returning it back, then unnecessarily this memory will be hanging without nobody to use it, right, and that is called memory leak. And we have to be very careful not to land up with memory leak, and that is one very important aspect of compilation that you will study in a full-fledged compiler course, but I am just giving you the thought process of how this can happen, right. Now, of course, after this keyboard.readint is completed, it actually reads an integer from the keyboard and it will put the integer read on top of the stack, which will be popped onto this variable length, so that this length assignment gets over. So this is something that we need to understand as a part of this. Okay, now what has happened? Now let us go back. Now you have a set of files, say for example main.jack, bat.jack, ball.jack. Let us say there are 3 jack files. We compile all of them to get each one of them to get main.vm, bat.vm, ball.vm with this. Now first and foremost, these main, bat and ball can also use some of the OS routines. If you use the VM emulator that is available in your tools directory, you go and click on the directory that actually stores this 3 .vm files. It will load all the VM files and it will assume it has inbuilt OS functionalities. The VM emulator has all the OS functionalities are inbuilt, so you need not put it as part of your VM files. So you can execute this and see whether your program is executing correctly. Program execution can be first tested on the VM emulator. So as a part of your first part of your project 12, you go and see in the project 12 directory, you will have many such. If you go back to the project part of your directory, so project 11 of your directory, you see so many files on the project 11, average, complex array, so many directories. Go to each one of these directories, compile all the VM files there. So you compile main file, you compile using the compiler. So if you go to this complex array, you have main.jack. So compile this. Go to convert to bin, again you have main.jack. Similarly, go to Pong, you have bat, ball, main, Pong game. Compile all the VM files. Then similarly 7, you will get this. And then you can also see the square. Again you have main, square game. So all these 6 directories, the files you can compile. Basically now use your VM emulator first to check whether they are working correctly, right. Now that is the first step. So that is what we want you to do as a part of project 11, right. And that is, so now that you have finished the compiler, now you can compile all these files and see whether they are actually executing properly on the VM emulator, right. So that is something that you need to check up here. Okay. Now when that is done, once that is done, so this is over. Now your program is working correctly. Now you want to execute it on the, finally we have to execute it on the hardware simulator. So what you do is you put main.vm, bat.vm, ball.vm, everything together as a single file. And also, since they are all using all the VMs in the memory, take all the VMs in the OS directory into a single file, right. For example, you will have array.vm, keyboard.vm, math.vm, memory.vm, all these things you put into a single file, and then you create one massive executable file, and that is basically called exec.vm. That is the executable file. So this is called static linking. Now you can compile it using VM to assembly translator, it will get translated to assembly. Then you can assemble it using assembly to hack assembler. So finally you will get a .hack file which will have the entire program. This is basically what, and this, now you will find that for your machine that we have RAM 32K ROM. This is where all your instructions should be stored. If I just take all the VM files in the OS directory, that itself will come to 45K. Essentially, this executable that you are creating cannot execute on the ROM 32K. It is in this machine, the hack machine that you have created, this whole thing cannot execute because it will exceed the size of whatever you have as 32K. So that is the most important thing that we need to keep in mind, right. So now what I have done, at the time of compilation itself, I have put all the main, bat, ball and all the VMs in the OS directory together as a single file. This is done at the time of compilation, not at the time of execution. That is why this is called static linking, right. Now, so now by doing this static linking, what did we have? What did we land up? We have landed up with an executable that will not fit into our hack machine. This is typically what you are going to face in today's what we call as Internet of Things era. In Internet of Things era, we are going to see small embedded systems, and these embedded systems are going to have very less memory. So what we call as memory footprint. The memory footprint of your program should be small, that it fits into this small embedded memory, right. You will have something like 32 kilobyte, yes, 64 kilobytes, 256 kilobytes, and you have to put the whole thing inside this, right, and execute. So one of the biggest effort in embedded programming that any one of you, if you really go into a challenging problems in embedded programming in the IoT world, I hope many of you will go and you take inspiration from this course. I will be extremely happy, right. So if you basically do that, then one of the things that you will really land up there is the that you need to start writing code that will fit into small memory footprints, right. So we will, in the next 15 minutes of this course that's pending, we will just go and see how do you do such type of writing, right. So even before looking into it, in modern compilers, like when you take a full-fledged compiler course, you will learn the dual of this static linking, what we call as dynamic linking, right. You will learn something called dynamic linking. What is dynamic linking? So when you compile a program, like I have main.vm, bat.vm, ball.vm, I will just do a static linking of only main, bat and ball, because they are all part of my code. Then basically I will link them, I will assemble them, and then I will convert it to hack code. So I will have the machine code for main, bat and ball, right. That will be loaded into the memory. So I will have one executable which have only main, bat and ball, okay. Now when this program is executing, whenever it calls a OS routine like array.new or whatever, the moment it starts calling, the operating system, that will go to the operating system, and the operating system will fetch that array.new function. Instead of that belonging to the original code, the operating system will fetch it into the memory, that function alone, execute it and throw it back, return it back. So on demand I can link with that function, get it executed. After that I don't need it, I can throw it back. Again, whenever I need, I can bring it. So it is not that I can bring only that function. for example, if you take string dot new, already we saw string dot new will call memory dot alloc. Okay. So, memory dot alloc may call sys dot error. So I bring, if I want to execute string dot new, first I will bring string dot new, I will start executing it. In the middle, when there is a memory dot alloc needed, I will bring memory dot alloc and execute that, and after it finishes I will throw off memory dot alloc. Then I will go and bring, so memory dot alloc in turn will ask sys dot error, I will bring sys dot error, but sys dot error, once this is getting over, I will throw it off, and then memory dot alloc when it gets over. So on demand I will bring the function from the memory to the from the storage to the memory and then return it back. So my memory footprint can essentially remain small. So this is called dynamic linking, because we are linking to the functionalities of the operating system at execution. So the dynamic word comes because we are doing it at the time of execution. Okay. But in this course, whatever we have done so far, we do not have an operating system of that caliber which can help us do some dynamic linking. Typically all the IoT devices, the small Internet of Things devices that stays on your surveillance camera at your house, or it stays on the in the sensor that is basically measuring temperature in your air conditioning unit or wherever, those things cannot afford to have an operating system. So we have to basically write small C code like what we are doing. It will be typically like a hack machine, right? And so how do we basically write code for hack machines, right? Hack such machines. So this is one case study that we would like to do now as a part of the remaining 2 modules. Thank you very much.